Welcome to the mathematics class, students. Let us discuss the indefinite integrals session 5 and 6. And the aim of this session is to define the successive reduction process to find the integration. Using that, we'll find out the successive reduction formulae, and also we'll see the definition of some rational standard form functions whose integrals exist and the related problems. First of all, let us go to the theory part related to the successive reduction. Here, evaluation of various forms of integrals by use of successive reduction formulae. Why do you need the successive reduction? When an integral involving two or more real functions and the two variables, say m and n, being m and n, let us take natural numbers as parameters, which is denoted by, say, imn or inm. That is, if you take imn as the integral of a function of f of x, g of x, and etc. up to m and n dx, and r is a real function of these ingredients contained in it, like e, f of x, g of x, etc. There you require to find the integral by means of successive reduction. And also an algebraic relation which expresses a higher index integral in terms of a lower index integral is called a reduction formula. Roughly, we define the reduction formula in this way. Reduction formula can be defined as an algebraic expression which expresses a higher index integral in terms of a lower index integral. This is called a reduction formula. This reduction formula is denoted by like in, and it can be completely evaluated by successively reducing the values of this index n. This process is called the integration by successive reduction. When you reduce such integral, which is the algebraic expression, expresses the higher index integral in terms of a lower index integral, then the successive reduction of this n will give you the process of successive reduction. The process of successive reduction is that we'll have some standard integral by means of the process of successive reduction. Here we go with the standard integrals. Number 1. The very first standard integral is if in is equals to integral of x to the power of n into e power ax dx, then this in can be expressed as 1 by a times of x power n e power ax minus of n by a I of n minus 1 for all n is natural number. Now see the proof of this formula. In is the algebraic relation which has a higher index integral in terms of the lower index integral. Integral of x to the power of n e power ax dx. Obviously, we'll take this as first function, it as second, then there is x power n of integral e to the power of ax is e to the power of ax by a minus integral of derivative of x power n is n into x power n minus 1 into e power ax by a dx. Thus it becomes 1 by a times of x power n into e power ax minus n by a into integral of x power n minus 1 into e power ax dx. If in is this one, then this is in terms of n minus 1. So obviously you can express that in terms of n minus 1 as n by a of in minus 1. So in is expressed in terms of 1 by a x power n e power ax minus n by a in minus 1. So this is the first reduction principle. Say here if you require to find I naught, that stands for integral of x to the power of 0 of e power ax dx, and it simply is equal to e power ax by a plus the integration constant k. This is what is I naught, and such a specific values you can find out using it. The second reduction principle is if in is integral of sine to the power of n x dx for all n being natural number, then we have relation like in equal to minus of sine to the power of n minus 1 x into cos of x by n plus n minus 1 by n of in minus 2 for all n takes values from 2 onwards. This is second reduction principle. Let us see the proof of the second reduction principle. Given is inth is equals to integral of sine power n of x dx. This can be written as integral of sine to the power of n minus 1 into x of sine of x dx. So this one as first function and this one as second. We'll get the first function into integral of sine is minus of cos x minus integral of derivative of first function n minus 1 times of sine power n minus 2 index changes and sin x in derivative is cos of x into integral of sin x is minus cos of x dx, which is equal to minus of sine to the power of n minus 1 x into cos of x minus into this minus become plus n minus 1 times of cos square. I can write as 1 minus sine square sine power n minus 2x into 1 minus sine square x dx, which is equal to minus of sine to the power of n minus 1x into cos of x plus n minus 1 times of integral of sine to the power of n minus 2x dx minus of n minus 1 times of sine to the power of n minus 2 multiplied with sine square sine power nx dx. So therefore this is minus of sine to the power of n minus 1x into cos of x plus n minus 1. This is in terms of in minus 2 and obvious this is in terms of in where this is in. So therefore you can write it as in plus n minus 1 times of in is equals to minus of cos of x into sine to the power of n minus 1x plus n minus 1 times of in minus 2. Therefore the integral inth is equal to integral of sine to the power of nx dx is given by, here 1 gets cancelled, n goes that side, therefore minus sine to the power of n minus 1x into cos of x by n plus n minus 1 by n in minus 2. This is the second reduction principle. Similarly proceeding, we can derive the third reduction principle as integral of, that is inth is equal to integral of cos to the power of nx dx as inth is equals to cos power n minus 1 x times of sine of x by n plus n minus 1 by n of in minus 2. The second reduction principle. The proof is similar to the previous one. And fourth one in terms of tan, that is inth is equals to integral of tan x power n dx. Then this can be is equal to tan to the power of n minus 1 x by n minus 1 minus of in minus 2. This is the fourth reduction principle. Let us find proof of this one. Given inth is equals to integral of tan to the power of nx dx can be written as integral of tan power n minus 2 of x into tan square of x dx. Therefore this inth can be written as integral of tan to the power of n minus 2x into tan square x. I can write it as secant square x minus 1 dx. If I can split this one, integral of tan to the power of n minus 1x into secant square x dx of tan to the power of n minus 2 of x dx. So obvious here this is in the form of integral of f of x power n into f dash of x is obviously f of x power n plus 1 by n plus 1. Therefore this can be written as tan to the power of n minus 2 plus 1 is n minus 1 by n minus 1 minus of this is in minus 2. So therefore here inth is written as, that is inth integral of tan to the power of n of x dx is tan to the power of n minus 1 x by n minus 1 minus of in minus 2 will be the fourth reduction principle. Similarly, we can write the fifth reduction principle, that is integral of, where in is taken as integral of cot power nx dx as minus of cot to the power of n minus 1 cot x to the power of n minus 1 x by n minus 1 minus in minus 2. This is the fifth reduction principle. Proof is similar to the previous one. Now the sixth one is inth is equals to integral of secant power n dx, which can be written as secant to the power of n minus 2x times of tan x by n minus 1 plus n minus 2 by n minus 1 of in minus 2. This is the sixth reduction principle. The proof we carry out is in this way, that is, let us consider inth is equal to integral of secant to the power of nx dx, which can be written as integral of secant power n minus 2 and secant square x dx. So it is the first function and it is second as it's integrable, implies secant to the power of n minus 2x first function into integral of secant square is tan x minus integral of derivative of this one is n minus 2 times of secant to the power of n minus 3x into derivative of secant x is secant x tan x into integral of secant square is tan of x whole dx. That is become secant power n minus 2 of x into tan of x minus n minus 2 is constant taken outside, secant power n minus 3 into secant x is secant power n minus 2 of x into tan square x. The tan square x is split in the form of secant square x minus 1 dx for better conclusion. That is secant to the power of n minus 2 of x into tan of x minus of n minus 2 integral secant to the power of n minus 2 with secant square x is secant power nx dx. This minus into this minus become plus n minus 2 of integral secant to the power of n minus 2x dx. Therefore this is in and here this is in minus 2. So we can express in is equals to secant power n minus 2 of x into tan of x minus n minus 2 of in plus n minus 2 of in minus 2. If this minus of n minus 2 in is taken this side, in 1 plus n minus 2 is equal to secant power n minus 2 of x into tan of x plus n minus 2 of in minus 2. Therefore inth is equals to integral of secant to the power of nx dx is this n minus 1 comes to the denominator secant power n minus 2 of x into tan of x by n minus 1 plus n minus 2 by n minus 1 of in minus 2. So this is the sixth reduction principle. Similarly, we can write the seventh reduction principle as like inth is equals to integral of cosecant to the power of nx dx, which is equals to minus of cosecant to the power of n minus 2x into cot of x by n minus 1 plus n minus 2 by n minus 1 of in minus 2. This is the seventh reduction principle. The proof is similar to the previous one. Next, the last eighth reduction principle is if at all imn, as we discussed earlier, parameters m and n are parameters, integral of sine power mx into cos power nx dx, then we have the following things to conclude. Let us say number 1 is imn can be put in the form of sine to the power of m plus 1x into cos to the power of n minus 1x by m plus n minus 1 by m plus n times of im n minus 2. Second one, imn can also be written as minus of sine to the power of m minus 1x into cos power n plus 1x by m plus n plus m minus 1 by m plus n of im minus 2 of n. And the third one is if at all imn is integral of x power m times of log of x whole power n dx, for all m and n are being natural numbers, imn can be written as x to the power of m plus n by m plus 1, x to the power of m plus 1 by m plus 1 times of log x power n minus n by m plus 1 of im and n minus 1. So these are the things. Let us find this proof. Now their proofs will find out in this way. Now the first one, that is imn is given as integral of sine to the power of mx and cos power nx dx. To show the first one, we'll consider this in this way. Let me write sine to the power of mx as it is, but cos I'll write as cos n minus 1x into cos of x dx. Now taking this as the first function, this as second, I'll get it as first function sine power mx into cos power n minus 1x into integral of cos of x. Integral of cos of x is simply sin x minus integral of its derivative. Its derivative is, say, sin power mx into derivative of cos n minus 1 times of cos power n minus 2x into derivative of cos is minus sin x. This derivative I am finding plus cos power n minus 1x into m into sin to the power of m minus 1x into sin x, derivative is cos of x. This total is multiplied by the integral of cos of x, that is sin of x into dx. Thereby this becomes a sin power mx into cos power n minus 1x into sin of x minus here n minus 1 and here m. So if I take this sin x into sin x, sin square x, and that sin square is written as 1 minus cos square, become plus of n minus 1 times of sin power m into x cos power n minus 2x into 1 minus cos square x dx separated. Again this is minus into this plus become minus m times of integral. This is cos power n minus 1 into cos x is cos power nx. Sin into this one is sin power mx dx. This is nothing but imn. And here I am going to get something, that is sin to the power of mx cos power n minus 1x into sin of x plus n minus 1 times of sin power mx into cos to the power of n minus 2x dx and minus of n minus 1 into sin power mx into cos power n minus 2 into cos square x is cos to the power of nx minus m into imn. This total is imn. So this one goes that side and this one also goes that side, that is imn of 1 plus n minus 1 plus m is equals to sin power mx into cos to the power of n minus 1x into sin of x plus n minus 1 into im but n minus 2. Therefore here we have imn is equals to, here 1 gets away, 1 plus n, so sin power m x cos power n minus 1x by m plus n plus of n minus 1 by m plus n of im n minus 2 is proved. Next let us go to the second one. Given imn is equals to integral of sin to the power of mx into cos power nx dx. To prove the second one, I'll write this one as sin power m minus 1 into x cos power nx into sin of x. Again this is first and it is second function becomes sin power m minus 1x into cos power nx of integral of sin of x is minus of cos x minus of integral of derivative of this one. The derivative of this one is m minus 1 times of sin power m minus 2 into sin derivative is cos into cos power nx plus n into cos power n minus 1x into cos derivative is minus sin x into sin to the power of m minus 1 into x. This is total multiplied by the integral of sin x is minus cos x dx. Implies this is minus of cos power n plus 1 of x into sin to the power of m minus 1x minus m minus 1 into this minus become plus cos into this cos square. So integral of sin to the power of m minus 2 of x into cos to the power of nx into 1 minus sin square of x dx, then plus into this minus into this minus become plus, and here we have now minus cos x into minus sin x is plus, but this minus make this one minus and n times of Cos power n minus 1 into cos x is cos to the power of n of x. Sin power m minus 1 into sin of x is sin power m of x into dx. Further, this is minus of cos power n plus 1 of x into sin of m minus 1 of x plus m minus 1 of this 1 into this one is integral sin to the power of m minus 2x into cos to the power of n x dx minus of m minus 1 into integral of sin to the power of m minus 2 into sin square is sin power mx into cos to the power of n minus of n into this is imn already, this also imn going to be. Therefore here we have imn is equals to minus of cos power n plus 1 of x into sin to the power of m minus 1 of x plus m minus 1 into im minus 2 of n minus of this is m minus 1 of imn and minus of n into imn. So if I bring all these imn together at one side, that is 1 plus m minus 1 plus n is equals to minus of cos power n plus 1 x sin to the power of m minus 1 x plus of m minus 1 of im minus 2 of n. So conclusion, that is here 1 plus 1 gets cancelled and leaves you imn times of m plus n is equals to minus of sin m minus 1 x into cos of n plus 1 x plus m minus 1 into im minus 2 and n. Therefore that is imn is equals to minus of cos power n plus 1 x into sin power m minus 1 x by m plus n plus m minus 1 by m plus n of im minus 2 of n. This is the second one. Now to prove third one, we have imn is equals to integral of x power m into log of x to the power of n dx, where m and n are natural numbers. So we'll write this as first, it as second, that is log of x to the power of n into integral of this one is x power m plus 1 by m plus 1 minus integral of derivative of log x power n is n into log of x to the power of n minus 1 by log x derivative into integral of this one is x power m plus 1 by m plus 1 dx. That implies x to the power of m plus 1 by m plus 1 times of log of x to the power of n minus of n by m plus 1 times of x to the power of m into log of x to the power of n minus 1 dx, where which can be written as x power m plus 1 by m plus 1 into log of x to the power of n minus n by m plus 1 of this is taken as im of n minus 1. So imn can be written as like this: x power m plus 1 by m plus 1 log x power n minus n by m plus 1 im n minus 1. Now we have an important note point here, that is if at all in is a integral like t power n by t square plus 1 dt, then in plus 2 is t power n plus 1 by n plus 1 minus in. So you are finding its higher order integrals. So therefore look out the proof of this one, that is given is in plus 2 will consider integral of t power n plus 2 by t square plus 1, because if in is this, in plus 2 must be this one. So therefore you can write it as integral of t power n by t square plus 1 and into t square. So write this one as t square, write integral of t square by t square plus 1 in the bracket t power n outside. Thereby here I can write it as t square plus 1 by t square plus 1 minus 1 by t square plus 1 separating into t power n dt. That implies integral of 1 dt, 1 into t power n is t power n dt minus of here t power n by t square plus 1 dt. Hence, here we have this is in plus 2. So in plus 2 is equals to integral of Tn. Integral of Tn is t power n plus 1 by n plus 1 minus this is nothing but in. So therefore we have proved that in plus 2 is equal to t power n plus 1 by n plus 1 minus in.